Hello everyone, my name is Nianyu Li. I'm a PhD student from Peking University. In this presentation, I will briefly describe the work collaborated with my colleagues Javier from University of York, David and Bradley from Carnegie Mellon University. The research topic is reasoning about when to provide explanation for human-involved self-adaptive systems. Okay, let's start. Software system was initially designed and developed to satisfy user requirement or system objective. However, such system would require frequent human intervention because the system was not designed to deal with uncertainty. So, a system administrator has to be there to monitor the system for some unusual conditions and works with the system to ensure its normal operation. This is the very first stage of system development. We often call it pre-adaptive era. Unfortunately, human error accounts for over 40% of system failures. Also, humans are very expensive, often comprising a large percentage of operating cost. And these reasons lead to an revolution on the system development. So we came to the self-adaptive era, which started around 2 decades ago. And the core idea of self-adaptive system is that it can evaluate its own behavior and changes its behavior when the evaluation indicates that the system does not achieve what it is intended to do or when better performance is possible. And the ultimate goal of self-adaptive system or automated system is to eliminate the need for human intervention while adapting to the changing circumstances. However, every coin has two sides. Even though humans are easy to make mistakes, they are not useless. Actually, humans can provide some expertise which is not easily automated. For example, there is a very famous saying in Wall Street. When the taxi driver is talking about the stock market, you know it's time to short. Well, you cannot imagine the system could smell the market like an expert dealer. Also, humans can detect problems that the system may not be aware of. So, systems can actually benefit a lot from some human involvement. As a result, we came to the third era, the co-adaptive era in recent years. In this new era, human and self-adaptive systems will collaborate to achieve their objective together with their diversity of skills, abilities, and availabilities. For a self-adaptive system, the most popular adaptive mechanism is the feedback loop. Basically, the dynamics generated by the environment or some certain events from their system are periodically monitored by the sensors. The controller then could analyze the available actions and their potential impact on the satisfaction of user requirement based on the models from the knowledge base, and plan adaptation decisions, which is to be enacted by the actuators. Let's look at how humans could involve in a variety of ways in this feedback loop. Typically, monitor can receive information from human who is acting as a comprehensive sensor. Human can indicate whether there is an ongoing anomaly based on the context information, which is not available to the system. The controller can incorporate the inputs from some domain expert who have additional insight about the best way of adapting the system. Executor can employ human as the system-level actuator to execute adaptations which cannot be fully automated. Beyond that, the role of human can be supervisor, observing the activities carried out by the system and to determine whether they are appropriate or potentially erroneous. Enabling effective human-system collaboration, however, is challenging because humans may not fully understand the system state, system goal, or even rationale for carrying out their actions. That's why explanation is sometimes necessary to make human involvement more efficient, to improve human understanding and improve ability to cooperate with the system in this co-adaptive era. So, to involve human operator as a part of the system, we should introduce some human models in the knowledge base to capture the attributes of human that might affect the interactions with the system. We'll employ the widely used Opportunity, Willingness, Capability, this OWC model, which characterizes human attributes into three components. First, opportunity captures the applicability conditions for a tactic to be carried out, such as, is there an operator physically located on site? Second, willingness captures how likely the operator will carry out a particular task, which could be affected by the level of attention or user stress. Third, capability captures the likelihood of successfully carrying out a particular task, which is determined by such as the training level. While existing empirical user study has shown that explanations can help users gain more understanding of the rationale behind system decisions and become more likely to cooperate with the system once they understand the need to act, thus increasing the user willingness. Also, in the user study, explanation increases operators' awareness of the situation on which capability is also enhanced. So, human capability and willingness are assumed to be affected positively by an explanation as the explanation benefit. However, explanation is not for free. It also comes with cost. Operator may need time and energy to comprehend this information. So, with the cost and the benefits, it's not obvious when to use explanation as a tactic. Too much, system will be slow to respond to adaptation needs. Too little, human may not be as effective. That's why the system needs to balance and trade off the cost and the benefit an explanation brings. So, in this work, we're reasoning about when to provide explanation. Specifically, explanation can be used as a tactic, which can potentially improve the system utility. Then, probabilistic model tracking will be adopted to analyze the trade-offs of using explanation in an adaptation strategy. To illustrate our framework, we will use CNN.com news website under distributed denial of service attacks as our running example. In this example, the website servers can provide multimedia content to users, or could show only text content, which requires less computation but less user experience. A load balancer will distribute user requests to a lot of servers. Sometimes, website might experience spikes because of some popular events, such as Donald Trump's new trailer. In this case, the system can activate a new web server to share the load, or provide text-only service to deal with the spikes. However, the spikes could also be because of the malicious clients trying to exhaust system capacity and making system services unavailable to legitimate clients. In this case, the first two automated tactics cannot handle the malicious clients, but result in an unnecessary operating cost. However, an operator could be effective in dealing with this situation by identifying attackers and adding the malicious IP address to a blacklist, or limiting the rate of the request from malicious clients. We also identified 4 quality attributes for this scenario. First, response time describes the time between sending the request and receiving the response from the server. Second, user annoyance, due to the misidentification of legitimate clients as malicious clients by human-involved tactics. Third, cost usually is the resources used in the system, which is defined by the number of active servers here. Fourth, client maliciousness, which is the percentage of malicious clients in the system stealthily. The impact on different quality attributes of the 4 tactics is shown in this table. For example, tactic activating a server can cause a drastic reduction of response time, decreasing 1,000 milliseconds with a big increase of operating cost. However, this tactic has no impact on malicious clients or user annoyance. But following our previous work, Our approach to reasoning about explanation builds on a recent technique known as stochastic multiplayer games to quantitatively reason about explanation trade-offs and reason about when explanations should be provided under uncertainty. In stochastic multiplayer game, systems are modeled as a turn-based multiple-player game. Moreover, only one player can choose between actions in a given game state, and the outcome could be probabilistic. Players can follow strategies to either cooperate to achieve the same goal or compete to achieve their own goals. Model checking then enables reasoning about strategies optimizing an objective in probability or reward-based properties. Our system is modeled as a stochastic multiplayer game with 3 players, and here is the player definition. Player environment is in control of all the actions that the environment can take out of the system's and human's control, while player operator specifies the actions controlled by the human actor. Player system controls the actions that belong to the system, whose behavior is encoded in the following 4 processes. The first one captures the behavior of the system under control, and the rest 3 are the processes that capture different adaptation strategies to deal with the spikes, which will be elaborated later. And there is a global variable term, which is used to explicitly encode alternating terms between the environment, system, and operator players. We model the stochastic multiplayer game using the syntax of Prism language, and here is an exemplified command. Action denotes the synchronization between process. Guard is a predicate over the model variables. U is an update describing a transition that the process can make if the guard is true. An update is usually specified by giving the new values to the variables and has an assigned probability p. For environment player, for simplicity, we assume our environment model only keeps track of time. Variable t is in the scope between 0 and maximum time horizon. During its term, the environment will check if variable t has reached the end of the time frame, and if this is not the case, it increments the value of t 1 unit and transfers the term to system player. For the operator player, we explicitly model the human attributes in different variables. For example, opportunity is denoted as whether the human is on location and whether he is busy with something else. Willingness is initialized with some constant that represents the initial willingness a human has based on his current state. Capability denotes the likelihood of successfully carrying out a particular task, which is specified by the training level. And the relationship between the training level and capability is shown here in this capability function. In general, the capability is positively correlated with operator's training level. When the training level is less than 50, the capability increases slowly with the increase in training level. However, when the training level increases between 50 to 80, the capability increases rapidly. This may be because quantitative change can lead to qualitative change. However, when the training level continues to increase, the increase of capability will become smooth, as the potential rising space for capability is comparably less. There will be 4 tactics associated with operator player. The tactic explanation is the action of providing explanation to the operator before assigning him black hole or throttle tactic. To recap a little bit, black hole tactic is trying to identify the malicious client and add them into a blacklist, while tactic throttle is trying to limit the request rate from malicious clients. Note that we can provide explanation for every tactic, as the operator's capability and willingness to perform different tactics could be various, or different tactics would be assigned to different operators. For every tactic, there will be 3 different commands involved. Here I will just illustrate how tactic black hole explanation is modeled. The first one is called tactic trigger, which occurs in the following conditions. First, the counter for this explanation tactic is 0. meaning that this tactic is not being executed right now. Second, an operator is on location. Third, this operator is not busy. Fourth, the tactic has not been executed before. As a consequence, the operator will be set as busy and the counter will be set as 1, meaning that this tactic is activated. The second command describes how tactic makes progress. Basically, if the counter is active, which means greater than 0, but still has not reached the tactic's latency, the counter will be incremented in 1 time unit. Third, tactic completion. When the counter expires, the counter and task completion identification are reset. Capability and willingness will be updated according to the impact of the explanation on the human operator, and the busy status of the operator is set to false. The encoding used for other tactics related to human operator follows the same structure here. For the system player, there are 6 tactics. Tactic explanation will only affect the willingness and capability of a human operator, while the rest of 4 tactics will affect system's quality attributes with respect to a successful activation of tactic as shown in this table. The structure for the tactic related to the system process is very similar to those just described, including 3 steps: tactic trigger, tactic update, and tactic completion. The only difference is that when tactic complete, system variables such as response time, malicious client will be updated based on tactic impact on quality attributes. For example, when the system assigned the operator to perform black hole tactic and when the tactic complete, with the probability associated with the operator's willingness, variable response time, malicious client, and user annoyance will be updated with respect to a successful activation of this tactic. However, the variable update will be discounted by the capability. Besides, it is also discounted with penalty due to the explanation comprehension latency. This is because a long period of latency with high response time and a large percentage of malicious clients is intolerable. Furthermore, with the probability of 1 minus willingness, this tactic was assumed to be failed. With these tactics, we can encapsulate them into different strategies. Here are the 3 typical examples. Eliminated strategy will first notify an operator to do the black hole. If the settling time for this tactic expires, and if the intended effect is not observed, this strategy will notify another operator to execute the throttle tactic as a fallback. Eliminate with explanation strategy follows a similar structure, except explicitly providing the explanation before assigning tactics to the human. Strategy outcome is an automatic strategy, including tactic activating a new server and tactic reducing the fidelity to provide text-only content. To do the model checking, we will quantify the system objectives with utility functions and preferences. The formulas in Prism can compute utility based on utility function for different quality attributes. Here is an example about how to calculate the utility for the percentage of malicious client. This utility function simply means that the higher percentage of malicious client, the lower utility for these quality attributes. Next, reward structures will weigh different quality attributes against each other by using the preferences of a given scenario. We are considering 2 typical scenarios here. One is eliminating malicious client, as the weight to malicious client is significantly higher than the rest. Scenario 2 is to optimize the experience of a legitimate client with almost equal weights in all different quality attributes. With the modeling of all the players with tactics and strategies, we want to answer the following 2 questions. First, how can the outcome of adaptation with explanation be predicted for human-involved adaptive systems? Second, how can a self-adaptive system determine whether explanation should be provided to a human operator in a given situation? To answer these questions, we specified the property, which is encoded in our temporal logic as shown here, where the RGU is the reward structure described in the previous slide. End is a predicate that indicates the end of the decision execution period. Then we will use the model checker to find the strategy that can help us achieve the maximum accrued system utility. For the first scenario, these two plots illustrate the maximum accrued utility the system can achieve in strategy eliminate and strategy outcome, respectively, with different percentage of malicious clients and various training level. We can observe how eliminate could generate better results when both the percentage of malicious client and the training level are high. This is because the automated strategy cannot deal with attackers, while the operator with high capability could effectively identify the malicious clients. This plot shows the delta in utility between strategy eliminate with explanation and strategy eliminate without explanation. As we can see, the improvement obtained from explanation is significant, especially when there are a lot of malicious clients and when the operator's training level is intermediate. This is due to the potential high learning space for the operators in the middle training level, especially when they are giving an explanation. If we compare these three strategies, we get this plot. The red points are the situations where explanation could facilitate the accrued system utility. However, if we increase the explanation cost, which means the explanation comprehension latency, the result in this new plot shows that the explanation makes sense in less situations. This is because with the higher cost, it is less likely that the explanation benefits can outweigh its cost. To provide further context about under what conditions an explanation should be provided, we present these two plots examining the trade-offs between explanation cost and explanation effect. As we can see for a novice operator, the delta in utility between with explanation and without explanation increases a lot, with higher explanation effect and lower latency. However, for an expert operator, the delta could be negative, especially when the explanation latency increases. This is consistent with our intuition that trying to make an expert understand something that she already knows is just a waste of time, which can degrade the overall system utility. Here is the analysis result for scenario 2, optimizing the legitimate client experience. If you are interested and want to see more result descriptions, please refer to the paper because I don't have enough time to explain everything here in this presentation. But to summarize a little bit for our analysis result, we can conclude that, first, explanation could enhance the system utility when involving human operators, especially when they have intermediate training levels. Second, the cost of explanation can even have detrimental effects when operators are close to their top training level. Third, in different scenarios, explanation improves system utility across large regions of the state space. In this work, we presented an approach based on probabilistic model checking to determine when an explanation should be selected as an adaptation tactic in a human-evolved self-adaptive system. Although one limitation of our approach is that we did not directly correlate our analysis result with the actual system. However, our findings are supported by and consistent with existing empirical user study. A second limitation is the lack of a direct procedure for obtaining explanation effect on willingness and capability. Prior work suggests that the impact on the willingness can be obtained through facial expression, while the impact in capability can be traced through historical behaviors. Also, sensitivity analysis can be useful when the explanation effect cannot be determined with precision, but within a scope. Another limitation is that explanation comprehension time is not easy to predict, especially across different operators. One way to overcome this is by assigning the latency based on the complexity of information in an explanation. Also, we have a number of additional research directions, such as formulating the problem as a multi-objective optimization problem instead of a single objective problem, so that we can solve it with Pareto optimal solutions. Yeah, this is the end of this presentation. Thank you for your attention and hope you enjoy it.